Hello, AP Chemistry students. We're now in section 3.2 on the properties of solids. So our learning objective for this one is to explain the relationship among the macroscopic properties of a substance, the particulate level structure of the substance, and the interactions between these particles. So we're going to be looking at the nanoscale of things, the atoms and molecules, and how the interactions between them end up having a larger effect on the macro scale properties of the substance, the sort of larger general scale properties of the substance. So the properties of both liquids and solids can be explained by the strength and type of intermolecular or intramolecular forces involved. I've talked a bit about this already in terms of IMFs and how they hold covalent molecules together. And then I also talked about how Coulombic potential energy holds things like ionic substances together. And the stronger the forces that hold the substance together, the more energy is going to be needed to disrupt these forces. So if we're looking at like a solid becoming a liquid, becoming a gas, we're looking about adding more kinetic energy to the atoms, making them move around more, and the forces holding the things together start to weaken as the particles get more kinetic energy. And the stronger those forces are, the harder it is going to be to disrupt those forces and say turn a solid into a liquid. When a substance melts, the forces that are holding it together become fluid and dynamic, constantly moving and rearranging. So what I mean by that is like imagine you have two water molecules that have a hydrogen bond attaching themselves in, say, ice, and you start to put that ice in a warmer environment. Those water molecules are going to start to vibrate and move around, and the hydrogen bond forces of the substance as a whole are not going to break as the solid becomes liquids, but they become more dynamic in the sense that you imagine those two water molecules that are attached to each other, and then one moves away, and then another one kind of comes in and attaches, and those bonds are constantly being sort of broken and reformed, or not bonds, but those interactions. And this is more or less true for metallic and ionic substances as well, but the energy needed to disrupt the Coulombic forces in those cases are a lot higher. And then once we eventually turn a liquid into a gas, it's going to be different depending on what kind of substance we're looking at. If it's a molecule, we're going to have the IMFs being broken, the intermolecular forces that are holding the molecules together are going to be broken, but the covalent bonds within the molecule are going to be retained. But for ionic and metallic substances, we're completely overcoming those ionic and metallic bonds. So if they become a gas, they usually just become individual atoms. And if we look at this graph below, we can see some the varying melting and boiling points between different types of substances. So if we look at the table below, we see there's a couple like covalently bonded molecules like ethanol, ammonia, hydrogen chloride, and you can see that their melting points and boiling points are a lot lower than say something cesium bromide, which is an ionic substance. So you'll generally see that the ionic types of substances have very, very high melting and boiling points, whereas covalent molecules tend to have much lower. Unless they have hydrogen bonding, the molecules that have hydrogen bonding tend to have a bit higher points. Say you compare something like hydrogen chloride or methane, which are in the negatives for their boiling points, which means they're probably going to be gases at room temperature, and compare that to something like water, which boils at 100 degrees Celsius, or ethanol, which boils at 78.3 degrees Celsius. Another property that is related to this is the vapor pressure of a substance. So even if something is not boiling and the molecules and atoms involved aren't being vaporized and turned into the gas form, there will be some molecules and atoms that are just doing that anyways. And the vapor pressure is usually defined as how much of a substance has vaporized at a given temperature in a closed system. So we can imagine we have some liquid here in this closed container, and we have enough particles that are jumping out of the liquid. They have enough kinetic energy to overcome whatever forces are holding them together. Because even at a set temperature, not all of the particles within a substance are going to have the same amount of kinetic energy. So some will still be stuck there, but some will have enough energy to overcome those forces. And you can see here that they start to fill the headspace above where the liquid is. So the vapor pressure is kind of a measure of how much of the substance is able to do that and become vaporized. And things that have higher vapor pressure are usually going to be things that have weaker forces holding them together. So like weak IMFs holding a substance together is going to result in very high vapor pressure. But something like an ionic substance is going to have an extremely low vapor pressure because you're going to need a lot of energy to sort of casually overcome those forces, especially if the substance itself is not boiling. So with those ideas in mind, we're going to be looking at the properties of various types of solids. And we're going to be focusing on ionic solids, network covalent solids, which we haven't talked about yet, molecular solids, large biomolecules, and metallic solids. So let's start with the ionic solids. I already mentioned that they have high melting and boiling points and very low pressure due to these strong Coulombic forces. And we also talked briefly on the last test about how they are brittle. And the answer to that question on the test would have been about thinking about the ionic salt lattice, where we have positive, negative that are sort of repeating in this pattern. And they are oriented in a way that get them as far away from each other as possible. Like the positives and the negatives are going to be attracting each other, but then the negatives and the negatives and the positives are sort of out of distance to each other. But what makes them brittle is if you were to imagine you pushed all of these ions over one space, now all of a sudden all of the positives and all of the negatives would be next to each other. So any type of pressure can actually move these atoms around into a position where the like charge repulsion is going to start to break apart the molecule. So overall, ionic solids have high melting and boiling points, low vapor pressure, are brittle. And the other property that we're going to be talking about in regards to a lot of these different substances is the conductivity of the substance. So ionic substances can conduct electricity in certain cases. They do have the positive and negative charges, which allow charge to flow, but only if the atoms themselves are mobile, which means that conduction in an ionic solid or an ionic substance overall can only happen when the solid is melted or if it's dissolved in another solvent. If you think about there's always the idea that water is really conductive, that it conducts electricity. But if you had to have distilled water, it wouldn't conduct very much. What we actually think about when we think about water being highly conductive is water that has ionic solids dissolved in it. If you were to like test the conductivity of salt water versus like fresh water, the conductivity of salt water is going to be much, much higher. And that's because it has mobile ions that are moving around in the substance. So like here we have an example of a salt that is sort of dissolving, and here we have all these positive and negative charges that are flowing through it. And those can carry extra electrons through the material to make it conductive. So in summary here, ionic substances can only conduct electricity if they're melted, if they're in a liquid form where the atoms can move around, or if they're dissolved in another solvent, if they become aqueous. So network covalent solids, which, like I said, we haven't talked about yet, are basically what they sound like. They are atoms that are covalently bonded to each other, so they're sharing electrons, they're overlapping their molecular orbitals, but now they're doing it in a network. They're not doing it in a molecule. They end up forming a complex 3D lattice, much like metallic or ionic substances, but these tend to only happen with certain elements. So we see network covalent solids occurring in the pure forms of solid nonmetals and metalloids, and mostly just carbon and the metalloids. So carbon as a nonmetal is generally going to form network covalent solids, and I'll talk about some examples of that in a sec. And then all of the metalloids, which you can see here on this diagram as the brown squares in the diagonal line, like silicon, germanium, arsenic, these are going to tend to form network covalent solids, as well as binary combinations of nonmetals, like silicon dioxide or silicon carbide. Some good examples of this are pure silicon, which is usually used in computer chips, and then also carbon in its diamond form. Here we can see what these are called the unit cells. These are basically what you would, if you're going to make the network, you're going to take this cube and basically just stack it in every direction, and that's going to give you the overall network solid. Same for this here. You can see that the carbon diamond has sort of a tetrahedral arrangement. And these substances are going to have a very, very high melting or boiling point and are going to be very hard. They're going to be very sturdy due to having such strong bonds at fixed angles. Also, many network covalent substances are semiconductors. So what it means to be a semiconductor is something that's like all right at conducting a current, but not as good as something like a metal. But that's really important to silicon as it's used in computer chips, and semiconductors have a huge part in a lot of technology. So I talked about carbon being specifically in its diamond form in that last example, but carbon also comes in another form called graphite. And if you have the same elemental substance, but it can form a bunch of different structures that have different arrangement of atoms and then different physical properties as a result, these are called allotropes. And graphite has a unique makeup that even though it's still a network solid, like diamond, it's going to be much softer. So this is sort of an anomaly when it comes to network covalent substances. It's instead of being hard, it's going to be kind of soft and easy to not necessarily easy to manipulate, but easy to break. Because if you think about what graphite looks like, it has these hexagonal rings that are arranged in sheets. These are going to be attracted to each other with like London dispersion forces between them. You can't really see this in this diagram, but there are resonant double bonds within these hexagonal structures, and we talked a lot about how pi bonds in double bonds can help with London dispersion forces. But since it's these like little layered sheets of hexagonal rings, what makes it soft is that the intermolecular forces holding adjacent sheets together are kind of weak, so one sheet can easily be slid off of the top. And that's why graphite is used as pencil lead, because as you drag the tip of the graphite along the paper, different sheets of these hexagonal rings are going to be basically torn off of the solid and then put onto the paper. So now let's talk about molecular solids. Um, Molecular solids are basically just when you have a molecule and enough of those molecules that they can all bind together and make a solid. A good example of this is ice. Ice is a bunch of water molecules that have a strong enough interaction that holds them together and holds them in place. Another example is solid carbon dioxide, or what we know as dry ice. I think that's what this diagram here below is showing. You have like a carbon in the middle with two oxygens, and these are all going to be bound to each other through their IMFs. But since it's only intermolecular forces holding the substance together, they're generally going to have low melting and boiling points because IMFs are a lot easier to break than like the Coulombic forces in, say, an ionic substance. And generally, molecular solids don't conduct electricity since the electrons are strongly held to the atoms in the molecules. All of the electrons, all of the valence electrons for these molecules are being used to make the bonds between the atoms in the molecules themselves. So they're not going to be a lot of mobile charge to conduct a current through. And sometimes molecules and molecular solids can have molecules that are really large. A good example of this are what we know as polymers, which are long chains of various smaller molecules that have been linked together. So if you imagine here, we had like one unit that is now repeating in a chain, and they can arrange themselves in sheets or they can like tangle around themselves. Different arrangements of polymers result in different physical properties for the macro scale of the material. But good examples of these are like plastic and rubber, and then a lot of other things that are made from petroleum or like natural oils dug from the ground. Um, Another type of it's technically a molecular solid. It depends on the context of it, but large molecules, large biomolecules have sort of a similar situation. They're usually made up of polymer-like materials. Say for like proteins, they're made of chains of amino acids. You have lipids, which are like really interesting materials that have a polar head and a non-polar tail, and they sort of arrange themselves in sheets like this, where all the non-polar parts are attracted to each other through LDFs, and then all the polar parts are attracted to each other through dipole forces, and you end up what are called micelles, which are these like little spheres where the polar bits are on the edges and the non-polar bits are in the middle, and that's what makes up these cell walls of cells. And then you have nucleic acids, which are also just chains of molecules, and carbohydrates, which are sort of similar to lipids, but they're like chains of sugars. And the shape and polarity of the different parts of these molecules are going to determine what its structure is and what its functionality is. So I talked a little bit about proteins in the last one, but proteins in particular are a pretty interesting biomolecule. You have this long chain of amino acids that sort of coils and wraps around itself, forming like helices and knots. And you have like specific intermolecular force interactions between different parts of it that end up making different pockets, exposing different parts of the amino acids. And the overall like structure of the protein ends up determining its function because proteins are enzymes. They are large biomolecules that catalyze reactions within the cell. And if you have like a pocket due to the structure, molecules can go in that pocket and then sort of interact with the various parts of the amino acids. So the structure of how it folds together ends up having a large effect on the overall property and function of the molecule. And another interesting thing about proteins is they are or proteins and other biomolecules is that they're pretty sensitive to temperature, because as these chains start to wiggle, those intermolecular forces holding those different parts together and making the overall macrostructure, they start to loosen up, and you end up unraveling your chain sometime. And this is called denaturation. And you might know this best from your own personal experience of frying an egg. So when you have an egg, you have this like sort of soft, fluidy material that has all these sort of proteins floating around. And as you heat it up, the protein unfolds and starts to make these unwound chains that start to interact with each other in sheets. And that's what happens when the egg gets firm, it gets cooked. So we also have metallic solids, which I think is the last one we'll be talking about for this video. We already talked a lot about how metals are made up of 3D lattices of metal atoms, or different types of metal atoms, and they're sort of surrounded by this sea of mobile electrons. And we talked a lot about in the previous slides about how conductivity is related to the mobility of charge. So that's why metals are the best conductors of all of the different types of solids, is because it already has this free-flowing sea of electrons with between the metal atoms. It's perfect for allowing charge to flow through it, because the electrons that you would hook up to the metal can just jump into the sea and move through the material, much like the electrons that are already there. And generally, metals have much higher boiling and melting points than, say, molecular solids or large biomolecules, or polymers and things like that, but they're nowhere near as high as the melting points and boiling points of ionic solids or network covalent substances, because they don't have as strong interactions holding the atoms together. And the metal atoms within the metallic structure are able to be moved around as a result. So we talked a bit about how metals are malleable and ductile. So malleable means they can be pressed or flattened. So you could take a brick of metal and you could like take a hammer and smack it until you flatten it into a sheet, and it is overall fine with that. Like, it's usually not going to crack. And ductile means you could be stretched into a wire. So you could take a chunk of copper and then slowly like kind of melt it down and stretch it out, and you can get a copper wire that's going to have the same sort of structural integrity as the material originally did. So these are two specific properties of metals that other properties or that other solids don't have. And it has largely to do with the structure again, because I'm able to move these metal atoms around and not force them to repel each other, because there's all these electrons sort of in between. They're kind of adding like a softening effect, like a buffer effect. So if this atom gets pushed in this direction, it's not going to end up repelling this other one, because there's all these attractive electrons in between. And we talked about alloys and how there could be interstitial alloys and substitutional alloys. And interstitial alloys, in particular, whoop, there's a typo here, sort of trade out that malleability and ductility that pure metals have, or some substitutional alloys have, because once you throw these little atoms into the like empty spaces in between the larger structure, it makes it a lot harder for the atoms to move around. But this is good in the case of using metal as a construction material. And that's why steel, which is a interstitial alloy, since the carbon atoms are much smaller than the iron atoms, end up being a really good material for building vehicles and support structures for buildings, because putting these small atoms in between the larger atoms makes it really hard for these atoms to move around. It almost acts more like an ionic substance in that point, where the atoms are in more fixed locations, but without the strong Coulombic forces that ionic substances have, but then also without the brittleness. So that's why they're really good for making structures out of. And that is all I have to say today on the properties of solids, and I'll see you in the next video.